Okay, we are ready for what I think is the last talk today. Lennart Klebl will tell us about Bernal stacked bilayer graphene. Please, go ahead.
Thank you for the introduction, and thanks to the organizers who are not here anymore for having me as a speaker at this wonderful conference. It has been so far very, very exciting and very many interesting topics and talks to listen to. And unfortunately, my projects about Kagome metals haven't reached the stage to be presentable at this time, so I had to resort to presenting something else to you. But I think for some of the crowd, this might be very interesting because it's a very generic model building question on systems with small Fermi surfaces that display all kinds of interesting correlation effects. And I will try to walk you through the example of Bernal bilayer graphene, so just two layers of graphene stacked on top of each other in the most energetically favorable stacking, which is A-B stacking. This has been joint work with a long-term colleague and friend of mine, Amon Fischer, who is currently finishing his PhD at RWTH University, and of course, the two of our supervisors. So Bernal bilayer graphene has emerged as a very interesting material in the last couple of years because starting in 2022, people have actually measured and cartographed, so to say, different strongly correlated states in that material. And it started with the observation of ferromagnetism in both the valley degrees and spin degrees of freedom in certain very low hole doping regimes of Bernal bilayer graphene under a transversal electric field. That electric field breaks inversion symmetry of the material and therefore creates some Lifshitz transitions, some von Hof singularities, and it is believed that in a way some of these instabilities could actually be weak coupling driven electronic instabilities. Very recently, some other charge instabilities have been discovered using STM in Bernal bilayer graphene, and here you see a picture of a Wigner crystal that is induced by a magnetic field that you put externally in Bernal bilayer graphene. And notice the scale bar here. I haven't put the actual scale, but this is 50 nanometers. So this is a huge length scale where you see charge ordering of that material, and it's expected that non-local electron-electron interactions play a very important role. And the length scale, furthermore, is that large because in reciprocal space, the Fermi surface of the material, or the pockets of the material, are tiny, which we're going to see shortly. Now, other experimental discoveries, of course, include superconductivity, and this is also one of the main points of focus for this material. So far, only superconductivity has discovered when inducing some kind of magnetic or S-spin orbit coupling into the material. So on the left, you see Bernal bilayer graphene put on top of a tungsten diselenide substrate, and the induced icing SOC leads to a superconducting region in one part of the phase diagram. So on the y-axis, you have, again, vertical displacement field. On the x-axis, you have hole doping, and the phase diagram is asymmetric because the setup is asymmetric. You have on one side the WSE2 that induces spin orbit coupling, and on the other side you don't. So only for doping carriers into the direction of the WSE2, you actually see this superconducting phase. And the interesting thing is that already here you can see the band structure in Bernal bilayer graphene and how it is modified by the proximity-induced spin orbit coupling. You see the trigonal warping features of Bernal bilayer graphene that under the electric fields gap out, and the holes display this valley flat band structure in a very small region in the Brillouin zone. So notice that this here is 0.05 in terms of reciprocal lattice vector. So it's 1/20th of the reciprocal lattice that you have this feature of the band structure. And the other observation is magnetic field-induced superconductivity. This is, in fact, only a very tiny region in the phase diagram. So here you have the, again, doping and electric field phase diagram under a magnetic field. And you see that somewhere in between those magnetic symmetry breaking phases, you have a superconductor that pops up. And as the phase is tiny and very close by to some magnetically ordered phases, you would expect that it could be a weak coupling electron-electron interaction-driven superconductor. Now, all of this is very nice, but from a theory perspective, it is very hard to model those materials. And that is because we have flat bands, flat sections of bands only in a very tiny part of the Brion zone. So here again, you see a picture of the band structure of Bernal bilayer graphene under a vertical electric field. And you see how the bands flatten in a tiny region around the K points, and you have Van Hove singularities in both the conduction and the valence band that kind of drift apart when you set the electric field larger. And here you see that you have various types of Fermi pockets at certain doping levels that are all controllable via external fields in those samples. I mean, this is the beauty of those 2D materials. And since energy scales are so low and the carrier concentrations are so low, all of this is easily achievable with external electric fields. So very highly tunable platform. And in terms of modeling, the complexity comes in due to the sheer small size of those Fermi pockets. So as I said, they are like 1/100th of a Brion zone or 1/20th of a Brion zone. And in principle, there's two ways how you can think about, yes, please? There's two ways you could think about modeling this. Either you could start from a ab initio simulation, do some Wannier interpolation, or write down a tight binding model, or actually figure out a tight binding model given the orbital content of your material, and then come up with a tight binding Hamiltonian. Here you see only in this very tiny region around the K point you actually reach the Fermi level. Or you could go the other way, do a K.P expansion, write a continuum model, and truncate it in some parts around the K and K prime points. Now, yes? Okay, I was unclear about this. Very, very good remark. It's easy to model the non-interaction properties. I would totally agree. But modeling interactions in this, without losing connection to real space, so the actual single carbon orbitals, is difficult when you have to resolve very tiny regions in momentum space, right? Because you have to do integrations over the Brion zone. You have to resolve all those greens and vertex functions in the full Brion zone, and that just gets super expensive. All right, yeah, so this talk's gonna kind of concentrate on the modeling aspect and try to answer the question if there is something else that kind of interpolates between the continuum picture where you have to truncate momentum space and can't use a lattice representation anymore, which is bad for many established many-body techniques, and the well-established DFT plus Wannier or tight binding perspective where you have the problem of needing to resolve huge Brion zones with high resolutions. So some merits and challenges for the DFT and Wannier approach. You have, of course, a symmetric lattice model that's directly baked into how you set up the model. And due to this, the DFT and Wannier models are accessible by state-of-the-art many-body techniques. So that would include tensor networks, DMRG, DMFT, FRG, et cetera, et cetera. And last but not least, you have the possibility to write down ab initio motivated interaction profiles. So this would be an example of a dual-gated Coulomb interaction that is both screened long and short range. And it's very easy to write that down in real space for a tight binding model. You can even go ahead and project some actual 1/r to your Wannier functions you get out from DFT plus Wannierization. So you have all the power of actually taking your actual realistic Coulomb interaction and seeing what it boils down to in the effective model. On the other hand, which is what Julian already asked, and I only put up here, you have very tiny and valley localized Fermi surfaces, at least in those graphitic systems, which makes it hard to model the full Brion zone and also at the same time the Fermi surface. And this leads to the requirement of horrendous momentum resolutions for momentum for any quantity in simulations of the interacting problem. On the other hand, continuum models directly have a very efficient valley local representation in momentum space. So you only care about those portions of the Brion zone where all your low energy states, electronic states lie. And in Bernal bilayer graphene, those lie around the valleys K and K prime. You only model a tiny region around those valleys and you have all the low energy excitations. And of course, non-interaction properties are very straightforward to calculate using this approach. And actually even more efficient than in a tight binding model because you only need very few degrees of freedom to write down this K.P model. But The problem is established many-body techniques require a lattice description oftentimes. For example, as Stefan said in his last talk, he talked a bit about the truncated unity FRG. And for this to work, you actually need a lattice to put your real space expansion of the vertex functions on. And this wouldn't work in a continuum model because you don't know at which length scale to truncate momentum space. And on the other hand, the other disadvantage of continuum modeling is that it's hard to do ab initio estimation of local interaction terms. For example, a Wally-Hund's coupling, so some kind of interorbital coupling between Wannier functions or states corresponding to different valleys is difficult to motivate in a continuum setting because you don't know which real space wave function actually corresponds to those states you're looking at. And one example I want to bring up where we were successful in doing the atomistic modeling, atomistic way of modeling those structures is the discovery of ABCB stacked tetralayer graphene. So recently, the experimental group at Aachen University discovered that actually they can see ABCB stacked tetralayer graphene using scanning near-field optical microscopy. And we did some atomistic simulations that confirm the optical conductivity and actually strongly confirm that this is going to be this type of stacking. They also find other types of stacking, the 3 different inequivalent stacking types in the tetralayer graphene actually. And for all 3, it was a straightforward task using the DFT-inspired tight binding model to describe those optical conductivities and unambiguously state which of them should be ABCB. We also continued to do some analysis of the possible superconducting and spin density wave orders in ABCB graphene. The nice thing about ABCB graphene is that without an external displacement field, since you break inversion symmetry already on the crystal structural level, you have valley flat bands and van Hove singularities that are rather strong in the non-interacting band structure without any need of an external field. And we went through all the sweat and pain to actually do the atomistic modeling on the RPA level, which is extremely costly, as I tried to say before, and find how those local and non-local interactions, Coulomb interactions, can actually lead to spin and charge fluctuation-driven superconductivity. So this is something like RPA Kuhn-Luttinger and a combined theory. If you want any more details, I'm very happy to talk to you about this. But this should be just an example of how atomistic modeling can be successfully applied, but it's really difficult and it's really costly, and going to a unbiased method for this kind of problem would have been impossible. So we really had to use the fact that RPA gives us some numerical freedom and gives us some performance in order to be able to do these simulations. Now, as on a side note, we found that local interactions strongly drive F-wave superconductivity in this material, which is a gap that looks like this here around the 2 valleys, whereas long-range Coulomb interactions drive P and D-wave superconductivity with, they're almost degenerate. And the reason for that is that long-range interactions in momentum space actually are interactions that work within a single pocket around, within a single Fermi pocket in a single valley, and therefore you need a sign change in the single valley, whereas the local interactions, you can have the sign change in between valleys. Okay. Now, the central question of this talk is how to bridge between continuum and atomistic models, and in fact, how to take the advantages from both of these, and where do we land when we build a model that kind of has the merit of only treating a small sub-portion of momentum space, but also keeping the connection to ab initio calculations. And our idea was to go to a moire setup. So this is one time where using a moire setup is actually beneficial and not overcomplicating things, where we set up an artificial supercell that is just here a linear dimension of the primitive cells, and treat the model in terms of these supercell lattice vectors, supercell reciprocal lattice vectors that are now rescaled by a factor of 1 over the number of cells, and then look at the non-interacting properties as well as interactions on that supercell. Now, real space gets expanded, as I said, by a factor of ns, and momentum space gets folded back. And when you look at it like here in the real space picture on the left and the momentum space picture on the right, you actually see how you can plot, how you can stuff a lot of unit cells in the real space supercell, and here how you can stuff a lot of supercell Brion zones into the original primitive Brion zone. Now, a side note is that we take supercells that are divisible by 3 in terms of the original unit cell, and that is because then the supercell center, the gamma supercell point, coincides with the primitive cell valleys, and therefore all phase factors, etc., are trivially contained because everything we need to do is we need to look at the gamma point of the supercell. So this makes things particularly simple, but it's not a necessity. So this is just a technical simplification. What we do when you have our supercell, we take our first principal Hamiltonian. So this is a Wannierized DFT Hamiltonian with a certain set of symmetries. So we have rotation symmetries, we have spin symmetry, we have time reversal symmetry, and just plug it onto the supercell, and we get out, so this is the primitive cell, a band structure on the supercell, where you see that all those bands that we have here close to the values K and K prime are actually backfolded to the gamma supercell position, and you see a strong valley polarization, so this is red or this kind of cyan color, in all the energetic region where the low energy physics is kind of is there, so up to, I don't know, a window of roughly 1.2 electron volt, those states are strongly valley polarized, suggesting that a valley polarized basis is a good way to describe the system. And I mean, this is what continuum models do, right? So when you look on the left-hand side, you see the continuum version of the problem where you have valley polarized states all the way. And this is why we here only plot one valley, because the other one is separate, kind of separate from the first one. And of course, we can reproduce all the Fermiology that we saw in the first picture here. So we have Lifshitz transitions, we have von Hove singularities, et cetera, et cetera. It's all contained in there. And the interesting thing to note is that we can arrive at a similar length scale as the one that is considered in the continuum model by just taking a large enough supercell. So for all plots shown within the context of this talk, I will go to a 24 by 24 primitive cell supercell, and this is enough to resolve the length scales that are kind of present and significant in the continuum model you see on the left. And as I said, we have both valleys in the supercell model that are both backfolded to the gamma point, whereas in the continuum model, we stay at the K point, we have to truncate momentum space, we have one valley per truncation, so to say. And now the idea is to take this supercell band structure, take the first few connected bands, or only the first on the valence side and the other one on, the first on the valence side and the other one on the conduction side, and write down Wannier functions that reproduce the spectral weight of those first two bands in each valley. And then, of course, take those Wannier functions, localize them in a way, project the Hamiltonian onto them, and do all other fancy stuff. So we go ahead and first, before writing down the Wannier functions, try to actually use the valley symmetry of the model. And this we do by projecting the band structure to the atomistic valley operator that you can read up on in, for example, this reference. And this actually now quantifies that there is a emergent U1 valley symmetry at low electron hole density. So I was talking about this before, but we actually do the calculation and see that the expectation value of the valley operator is very close to 1 in the energy window that we want to do the Wannierization for. And then we go to the supercell point at gamma, which corresponds to the original K and K prime points. We take valley polarized Bloch functions from there, and we build wave packets from those Bloch functions. So we just take them, transform them to real space, set up a Gaussian that goes across this real space wave packet, and then we use those wave packets as trial functions for the Wannierization. And then there are some technical details can be discussed on a personal level. I think this is not suitable for the talk, but some iterative single-shot-like projection procedure to actually localize them even further and have a very local and well-localized basis. Yes?
Do you use all these remote bands, or are you throwing bands away?
I'll come to that in a second. So we have now, or maybe I'll answer the comment right now because it's probably better. We only take 1 at 2 Wannier functions per valley. So in total, it's going to be a 4-band model or a 2-band model per valley, meaning we throw away everything above, say, 0.3 electron volt or so. In principle, it would be easy to take more bands and to write down more states to get more of the high energy physics, but the idea is to write down an effective low energy model. Yeah, so the two Wannier functions we have now a degree of freedom on the orbital basis. So they can either be localized on the B2 or the A1 orbital, corresponding to the leftmost lower A side of the lower honeycomb lattice, or the rightmost upper B side of the upper honeycomb lattice. Of course, they have some weight on the other sides as well, but notably this here is a logarithmic color scale, so we really see that those Wannier functions are localized strongly within or around within one or two supercells. So the honeycomb you see here in white is the superlattice, or the supercells. And what we then do with these Wannier functions, we project them onto the original Bloch states. Now, this is the one Wannier functions course. The blue one is the Wannier function corresponding to the B2 orbital, and the red one is the one corresponding to the A1 orbital. And we see that they have most weight in the Bloch states around the supercell gamma point, which corresponds to the valley K of, or K prime of the original primitive cell. And the other one, of course, correspondingly has most weight in the conduction band, and together they reproduce most of the spectral weight of all the states close to zero energy. As a control, we have plotted the hopping parameters when projecting the Hamiltonian onto those Wannier states, and we see that they decay strongly exponentially, meaning that we have a well-localized Wannier basis for our problem for the Bernal bilayer graphene in the supercell. And what we can do now is we can take those Wannier functions at certain values of the vertical displacement field, which is shown here, and we interpolate the hoppings in between those gray points, and we see that we perfectly interpolate also the band structure that we get out as a result. So our method allows to efficiently calculate all band structures for several vertical displacement fields, and also perfectly reproduce the tight binding or continuum model band structures, which you see here faintly indicated as gray. And also here you see that we reproduce the Van Hove singularity, behavior, etc. So the last question to ask about those supercell Wannier functions and their transformation behavior is how they transform under symmetries, what kind of orbitals we actually wrote down. And we kind of have to disentangle the problem by taking our microscopic phase factors that stem from the valley degree of freedom and our macroscopic phase factors that are actually the phases of the Wannier functions. If we plot this in real space, again, this is the same plot as the red and blue one before for the absolute value, we see that we transform with with zero phase windings in the dominant orbital, one phase winding in the non-dominant dimer orbital, and then a double phase winding in the opposite orbital. And if we munch that together with the C3 eigenvalue of those atomic sites corresponding to those four panels, we actually end up with P plus minus orbitals that correspond to how those Wannier functions transform under C3 rotation symmetry. So we wrote down a P plus P minus orbital model for each valley of Bernal bilayer graphene. And we can try to connect this to the chiral quasiparticles that are known to exist in those rhombohedral graphene stacks. For instance, in J-layered rhombohedral graphene, it is known that the wave function between the leftmost bottom and the upmost, the topmost right orbital has a relative phase winding of j times pi, where j is the number of layers. So for instance, for Bernal bilayer graphene, you would really expect those double phase winding between those two orbitals that you sit on. Whereas for monolayer graphene, you would expect a single phase winding. For rhombohedral trilayer graphene, which would be ABC, you would expect a triple phase winding. And this is well reproduced within our Wannier functions, and the last thing to check is the Berry curvature, which arises due to those phase windings. And we see that, at least in a certain energy window, we really strongly reproduce all the features from the primitive cell model. So here on the left, you see the primitive cell Berry curvature, like overlaid onto a 3D counterplot of the dispersion. On the right-hand side, you see the Wannier function Berry curvature, so the Berry curvature of the projected Wannier model, and you see that it agrees well in a certain energy range. So if you imagine you cut here and here, you see it's perfectly the same. Although at higher energies, you have some mismatch, and this is for the same reason that you have mismatch here in the band structure. So the thick black lines are the Wannierized model, and the dotted gray lines are the supercell model. And you see that at the Brion zone edges, you get a mismatch because you write down a single or a 2-orbital model to reproduce the band structure of a connected set of bands. And this is also the reason for the Berry curvature being kind of different at the edges of the Brion zone. But at the center of the Brion zone, we perfectly reproduce what is actually there in the primitive cell model. Okay, having all of this together for the Bernal bilayer graphene, we can seek for extensions to other rhombohedral graphene stacks, and I'm just going to quickly showcase them, just with the reasoning that we know it works also for the other systems. So for monolayer graphene, we can write down those exponential localized Wannier functions in the same way. We get the phase winding, as I discussed before, with 0 and 1, and 1, 0 and 1, and we perfectly reproduce the parts of the band structure that are close to 0 energy. Also for rhombohedral trilayer graphene, same story. We now have a lot of orbitals, and the interesting thing to look at is exponential localization, checkbox. Then we have phase windings. This is not phase winding on the dominant orbital, and 3 times phase winding on the outermost orbital, and the band structure is reproduced again well. Okay, now what can we do with those Wannier functions? We can take an ab initio Coulomb interaction known from 2 sources. So the first one would be the short-range screening, which is of UNO type. So here you actually see that you regularize the R = 0 divergence with a kind of square root. And the other one would be a long-range dual-gated screening, where you regularize the 1/r tail, or the momentum space Q = 0 divergence, with some exponential written here in terms of Bessel functions of the second kind, I think. The point being that we can combine both of these behaviors to arrive at an interaction that is ab initio motivated, that is both short-range screened and long-range screened. And we actually take this interaction now and we project it to our supercell Wannier function. So we basically calculate those integrals, the first one being Hubbard interaction parameters, the second one being density-density interaction parameters, and the second one being all kinds of exchange interactions. And we clearly see that the interactions of this model are dominated by Hubbard-type interactions. So on the right-hand side, you see all the local interaction terms where U1 and U2 are intra-orbital Hubbard interactions, and U3 is the intra-orbital Hubbard interaction. All of those are much bigger than anything else, because here you have the second kind of Y scale for the Hund-type interactions. So the Hubbard interactions come out at roughly 80 MeV with the largest, and the Hund interactions, all those intra-orbital or intra-orbital inter-valley, or both intra-orbital and inter-valley Hund coupling, come out at maximum, say, 8 MeV, so a factor of 10 smaller than all Hubbard kind of interactions. And what we also see is that with screening distance for a certain size of the supercell, we actually can reproduce the exponential tail of the long-range part of the Coulomb interaction that we expect for all lengths that are greater than the screening distance. So we have a ab initio motivated model for all the interactions, all the repulsions for electrons in that system. And the very important point is that all of this places the model firmly in the weak coupling regime. So for a supercell size of 24 by 24 primitive cells in a single supercell, which is roughly like something around 6-7 nanometers in size, we have a ratio of interactions over bandwidth of roughly 0.15. So that makes it perfectly suited to weak coupling studies of that model. And with this, I would like to conclude my talk and summarize really quick what we achieved in this work. So we wrote down supercell Wannier functions for a very efficient low-energy lattice representation for rhombohedral graphene multilayers. Those are valid as long as the size of the supercell does not exceed the size given by the Fermi pocket. So the inverse of the Fermi pocket diameter must not exceed, must not be on the same order as the size of the supercell. Otherwise, you need to take more bands into account. There's a work that doesn't do Wannier projection, but does do something very similar. They write down a minimal model for the case where the supercell size is actually larger than the size given by the Fermi surface diameter. One point is that this kind of modeling is very straightforward to generalize for any kind of small Fermi pocket systems. Actually, Graphene is a difficult system to start with because you have those chiral quasiparticles to work with, and you have to be careful to include Berry curvature, etc. correctly. They're topologically non-trivial. There are other systems that are more easy, and for one example would be modulation-doped aluminum arsenide quantum wells, where you have very tiny Fermi pockets in the conduction band, and those can also be represented by supercell Wannier functions. And then you have a very interesting phase diagram of nematic states and symmetric phase states that kind of have a transition at a certain electron density in the system. We also managed to write down ab initio interaction profiles in this basis, and on a side note, we could further improve those by doing constrained RPA or even constrained FRG to write down the actual screened interaction in the effective model. And in general, we have now a framework to do ab initio motivated study of correlations in small Fermi pocket systems, which would include the question about the superconducting pairing glue in Bernal bilayer graphene, of course, spin and valley magnetism in Bernal bilayer graphene, and as I said before, nematicity in those aluminum arsenide quantum wells. And we're actively working on this using, which I shamelessly advertise here, our framework for functional RG simulations, which is open source since this year, to find all kinds of spin and spin valley polarized phases in Bernal bilayer graphene and also nematicity in those aluminum arsenide quantum wells. Thank you for your attention, and happy to answer any questions.
Thank you very much, Lennart, for a very interesting talk. We already have a question.
Thanks for the talk. So I think I missed something very basic. The first question was, what exactly was the advantage you gained from using this supercell numerically?
Oh, there is, for graphene, there is two advantages. The first one is we have a efficient representation of the valley degree of freedom, which you don't have in tight binding models because one band has both parts of the valley attached to it. Mm-hmm. And the second is you have just a much smaller Brion zone, making the Fermi pockets larger.
I see. So the Fermi pockets are just a larger percentage of the mini Brion zone in this expanded unit zone. Okay. The other question I had was, had you thought about trying to estimate the magnitude of spin orbit coupling from proximity to the TMD layer? Because it seems that at least in bilayer graphene, the spin orbit coupling is important for superconductivity.
We haven't done that yet. This is partially on the list for what is needed to do to make a statement about the superconducting pairing glue. The thing is that it is also seen under the application of a Zeeman field, so potentially it would be enough to include the Zeeman term and not the spin orbit coupling to see what works.
TC is much, much smaller when it's field induced. It's
yeah.
Thanks.
More question? Yes.
So you have the Wannier basis now. You can write down a tight binding model based on this. Have you? And you can look at effects of various interactions in that. Have you done this already?
No, not so. Very preliminary, but not finished. So we see some kind of spin valley polarized phase emerging at certain dopings and certain E fields, but we haven't finished the analysis. So
you have things like Hubbard-U in there?
Yeah. We have all kinds of so Hubbard-U and Hund's J and also long range.
Right.
Yeah. So they are all in there.
Question. So this spin valley polarized phase that you found in your numerics, what is that referring to? Is that like opposite spins and opposite valleys, or is that both spin and valley have been polarized? Or
it's an instability that is fourfold degenerate in the spin sector and twofold degenerate in the valley sector. No, twofold and twofold. Sorry. So you have basically all the possibilities to go into any direction in this combined spin valley U4 space.
Okay, so I have fourfold degeneracy to start with because I have two spins and two valleys, do I not? And so I polarize some subset of those degrees of freedom. And for spin polarization, I'm just throwing away half of the spin degrees of freedom. Yes. So what is it for spin valley polarization?
It depends. So we haven't done the mean field analysis, but we have a order parameter, a manifold of order parameters that is largely degenerate, and we have to find which direction the order parameter wants to go in. And this could be either just into a spin direction or into a spin and valley polarized direction. And the
So
SVP is both spin and valley
So
polarized.
SVP, you're saying there's a degeneracy between multiple possible
Yes.
polarizations. Is it all possible ones, or is there just a subset? Like, what is the submanifold that the red region indicates?
I have to admit, I'm not too sure about this.
Okay.
Potentially it's the full, but I don't know. I haven't done this myself, so.
Yes, more. You go one slide back, maybe. I think it was, I don't understand the green statement here. This one. I mean, how can isn't the number of supercells is something you decide, right?
Yes.
How can that number be affected by your choice of supercells? Shouldn't the regime you're in be something that doesn't depend on that?
I mean, at a certain point, you're kind of expecting to have something else happening because you're making the supercell so large that you have to take into account more bands than the one band we're taking account per valence or conduction band. So it's kind of expected to see something happening.
Okay, so this is equivalent maybe to my other question. This is related to the fact that you zoom in to that region and then maybe you have to, you're throwing away other bands.
Yeah.
Yeah, okay.
I mean, bandwidth is probably not the best parameter to compare to. Probably it's something like, I don't know.
Okay, yeah, I understand. W depends on NS.
Exactly.
Yeah. Okay, very cool. No, it's impressive. Any more comments, questions? People are ready for the swimming pool. Okay, let's thank Stefan and Lennart again, and then I think we close the session for today.